I remember the exact moment the data stream from the European Space Agency's Trace Gas Orbiter, the TGO, finalized its processing. It was late October, just after 3I Atlas had swung past its closest point to the Sun, its perihelion, and was finally emerging from the solar glare. For weeks, we had been blind, relying on the few instruments that could peer around the Sun's edge, like the stereo spacecraft. But the TGO, positioned in orbit around Mars, gave us a unique, high-resolution vantage point. The initial images were already extraordinary, showing a comet that had brightened far more than our models predicted, a truly explosive event of sublimation and dust ejection. But it was the spectral analysis, the color data, that truly stopped me cold. I saw the plot, the curve of reflected light across the visible spectrum, and it was undeniable. The coma of 3I Atlas had shifted. It was now displaying a distinct, faint bluish hue, a color that was, in fact, demonstrably bluer than the light of the Sun itself. This was not a trick of the filter, nor an artifact of the image processing. My team and I ran the calibration routines 3 times, cross-referencing the TGO's color and stereo surface imaging system, CASSIS, data with the concurrent observations from the ground-based telescopes that were just beginning to pick up the object again. The result held firm. The interstellar visitor, the third of its kind we have ever confirmed, had changed its spectral signature for the 3rd time since its discovery in July. I felt a profound sense of scientific awe mixed with a deep, almost unsettling curiosity. This object, which had traveled for billions of years from a star system unknown to us, was actively, dynamically rewriting its own surface chemistry right before our eyes, triggered by its brief, violent encounter with our star. The very nature of 3I Atlas is what makes this color shift so significant. I have spent my career studying comets, those icy relics of the solar system's formation, but this object is different. It is an interstellar interloper, a true vagabond ejected from its home system in the distant past. When I look at the data, I am not just looking at a chunk of ice and rock, I am looking at a pristine sample of a stellar nursery that is not our own. The material that makes up its nucleus has been preserved in the deep freeze of interstellar space, shielded from the thermal processing and radiation that has altered the comets native to our solar system. Its initial appearance, the first color we observed, was a deep, dusty red. I immediately recognized that signature. It was the color of complex organic molecules, the tholins, the tar-like substances that form when radiation acts on simple ices like methane and ethane. This red color told me that the surface layer, the crust that had protected the comet for eons, was rich in these complex, heavy molecules, a kind of interstellar sunblock. This was the first layer, the ancient skin of the object, and its redness was a direct chemical fingerprint of its long, cold journey. But as 3I Atlas plunged deeper into the inner solar system, the Sun's energy began to strip away that ancient crust. The red dust was ejected, forming the initial, massive coma. Then, in September, we saw the second, brief color change, a distinct, almost sickly green glow. This was a classic cometary phenomenon, one that I have seen countless times in our own solar system's comets, but it was still thrilling to see it on an interstellar object. The green is caused by a simple, diatomic molecule, a fragment of carbon that is released when more complex carbon-bearing molecules sublimate from the nucleus. As this fragment is exposed to the Sun's ultraviolet light, it absorbs the energy and then re-emits it almost instantaneously at a specific wavelength that our eyes perceive as green. It is a fleeting signature, a temporary chemical flash, because that diatomic carbon is highly unstable and quickly breaks down further. I knew then that we had breached the red crust and were beginning to access the more volatile ices beneath. The green was a window into the cometary interior, but it was only a brief glimpse. Now, we have the blue. This is the most compelling and scientifically rich of the 3 color shifts, and it is the one that has truly ignited the debate in the astronomical community. The blue coloration is not a reflection of sunlight off dust, nor is it the simple fluorescence of diatomic carbon. It is a signature of something far more volatile, far more energetic. The spectral analysis shows that the light being emitted is concentrated at the bluer end of the spectrum, a phenomenon that is often described as being bluer than the Sun. This is a critical distinction. It means the light is not merely reflected, it is being generated by a process within the coma itself, a process of molecular excitation and ionization. The leading hypothesis, the one my team and I are currently focused on, points to the sublimation of highly volatile ices, specifically frozen carbon monoxide and, potentially, ammonia. These molecules are typically locked deep within a comet's nucleus, requiring very little heat to transition directly from a solid to a gas. As 3I Atlas approached the Sun, the heat penetrated the nucleus, causing these ices to sublimate violently. The resulting gas molecules are then subjected to the intense solar wind and ultraviolet radiation. When a molecule of carbon monoxide, for instance, is hit by a high-energy photon from the Sun, it can be stripped of an electron, a process called photoionization. The resulting ion, a charged molecule, then interacts with the solar wind, and in that interaction, it emits light at a very specific, short wavelength, the blue light we are now observing. I find the sheer volume of this blue light-emitting material to be astonishing. The fact that the blue hue is so pronounced suggests that the interior of 3I Atlas is disproportionately rich in these supervolatiles compared to the comets we typically see. This is the key piece of evidence that speaks to its interstellar origin. In the outer reaches of our own solar system, in the Oort cloud, comets have been exposed to the Sun's influence, however slight, for billions of years. This long, slow thermal history would have gradually depleted the most volatile ices. But 3I Atlas, having spent its life in the much colder, darker environment between stars, has retained a massive reservoir of these ices. The blue color is the spectacular, luminous proof of that deep-frozen, alien chemistry being violently unleashed. The sheer scale of the sublimation event is also what explains the extreme brightening we observed while the comet was behind the Sun. The brightening was not a gradual increase. It was a sudden, dramatic surge, indicating a massive, non-uniform release of material. I believe this points directly to the cryovolcanism that has been widely discussed. Imagine the nucleus of the comet as a pressure cooker. The heat from the Sun penetrates the outer layers, turning the super-volatile ices into gas. This gas is trapped beneath the remaining crust, building up immense pressure. When the crust finally gives way, it doesn't just sublimate gently, it erupts in powerful, collimated jets, what we have termed ice volcanoes. These jets blast out a tremendous amount of gas and dust, dramatically increasing the surface area, reflecting sunlight, and, more importantly, flooding the coma with the carbon monoxide and ammonia that are now glowing blue. The color shift is, therefore, the spectral signature of a colossal cryovolcanic outburst. Of course, not every scientist agrees with this interpretation. I have colleagues who argue that the color change is not a change in the gas coma at all, but rather a change in the scattering properties of the dust particles. They suggest that the violent sublimation event simply shattered the larger, red dust grains into much smaller, finer particles. These smaller particles, according to the principles of light scattering, would preferentially scatter the shorter, bluer wavelengths of sunlight, making the coma appear blue without any fundamental change in the gas chemistry. I respect this viewpoint as it is a valid physical mechanism, but the spectral data, in my opinion, leans heavily toward the emission from ionized gas. The intensity and the specific wavelengths we are seeing are more consistent with a chemical glow than with simple light scattering. The debate is healthy, and it is precisely this kind of disagreement that drives us to seek more data, to refine our models, and to eventually arrive at a definitive conclusion. The non-gravitational acceleration we have measured is another piece of the puzzle that strongly supports the cryovolcanism and the blue light hypothesis. When a comet sublimates, the gas jets act like tiny thrusters, pushing the nucleus slightly off its purely gravitational path. For 3I Atlas, this non-gravitational force is significant, and its direction is highly irregular. This is not the steady, gentle push of uniform sublimation. It is the erratic, powerful thrust of those ice volcanoes firing off across the surface. The jets are not symmetrical, and their activity is not constant. I can correlate the periods of extreme brightening and the onset of the blue color with the most pronounced deviations in the comet's trajectory. The blue light is the visual manifestation of the chemical engine that is literally pushing this interstellar object through our solar system. The sheer complexity of the chemistry we are seeing is what makes 3I Atlas a treasure trove. The initial red color gave us the surface organics. The green gave us the dicarbon. The current blue is giving us the supervolatiles like carbon monoxide and ammonia. But there is more. Our instruments have also detected an unusual abundance of carbon dioxide and high levels of water leakage. The water is a given for any comet, But the carbon dioxide is particularly interesting. It is another volatile ice, but it sublimates at a slightly higher temperature than carbon monoxide. The presence of both, along with the other chemical signatures, paints a picture of a nucleus that is chemically zoned, a layered structure that has been preserved since its formation. I imagine the nucleus as a geological record, a frozen history book of its home star system, and the sun is now acting as a cosmic drill, exposing those layers one by one. The implications of this blue shift extend far beyond just the composition of one comet. I am looking at a chemical profile that is not typical of our solar system's formation. This object originated in a different stellar environment, a different molecular cloud, and its composition reflects the unique temperatures, pressures, and radiation fields of that distant place. The abundance of carbon monoxide, for example, suggests that the molecular cloud from which 3I Atlas formed was particularly rich in that molecule, or that the process of planetary formation in that system was far more efficient at trapping these volatiles than the process that formed our own solar system. Every photon of blue light we detect is a messenger, carrying information about the conditions of a star system that is now long behind this cosmic traveler. I find myself constantly thinking about the journey of this object. It has spent billions of years in the void, a tiny, frozen world drifting between the stars. The cosmic rays, the high-energy particles that permeate the galaxy, have been bombarding its surface for all that time. This bombardment is what created the initial red crust, the tholins, but it also had a deeper effect. It may have altered the crystalline structure of the water ice within the nucleus, making it more amorphous, more prone to the kind of explosive phase transitions that could fuel the cryovolcanism we are now observing. The blue color, therefore, is not just a sign of sublimation, it is a sign of a nucleus that has been fundamentally altered by its interstellar history, a history that is completely alien to our own solar system. The work we are doing now, tracking the blue shift and the associated activity, is a race against time. 3I Atlas is already past its closest approach to the Sun, and it is now heading out of the inner solar system. Its activity will soon begin to wane. The volatile ices will be depleted, the cryovolcanism will subside, and the blue glow will fade. The comet will return to its dormant, red-crusted state, a silent, dark traveler once again. But the data we are collecting now, in this brief window of intense activity, will be studied for decades. I am personally involved in the planning for the next phase of observation, which includes using the James Webb Space Telescope to get an infrared look at the gas and dust. The infrared spectrum will allow us to identify the heavier, more complex molecules that are not visible in the blue light, giving us an even more complete picture of this alien chemistry. The entire event, from the initial discovery to the current blue shift, has been a masterclass in cometary science. It has forced us to confront our assumptions about what a comet is and what it can do. The rapid changes in color, the extreme brightening, the evidence of powerful jets, all of it points to a level of dynamic activity that is unprecedented in our experience. I am a scientist, and my work is driven by data and verifiable facts, but I cannot deny the sense of wonder that comes with studying an object that has literally come from another world. The blue light is not just a spectral line, it is a beacon, a signal from the frontier of the Milky Way, telling us that the chemistry of the universe is far more varied and far more exciting than we ever imagined. I have to address the other fascinating, if slightly more controversial, observation: the anti-tail. Most comets have a single, beautiful tail of dust and gas that points away from the sun, pushed by the solar wind and radiation pressure. 3I Atlas has displayed this, but it also briefly showed an anti-tail, a faint spike of material that appeared to point toward the sun. I know this sounds counterintuitive, but the explanation is purely mechanical, a trick of perspective. The anti-tail is not material being pushed toward the sun, it is simply larger, heavier dust particles that were ejected earlier and are now orbiting the sun on a slightly different path than the nucleus. Because of our viewing angle from Earth, these particles appear to trail ahead of the comet, giving the illusion of a tail pointing the wrong way. The anti-tail is, in fact, a testament to the sheer quantity of dust that was ejected during the initial, red-hued phase of activity. It is a fossil record of the comet's past outburst, now being illuminated by the very star that caused it. The current blue color, however, is all about the gas. The ionized gas, the carbon monoxide and ammonia ions, are so light that they are immediately swept away by the solar wind, forming the classic, straight, blue ion tail that is now dominating the comet's appearance. The contrast between the heavy, red dust of the past and the light, blue gas of the present, is a perfect illustration of the comet's evolution as it interacts with the Sun. I am watching a geological and chemical transformation unfold in real time, a process that has been dormant for billions of years and is now being compressed into a few short months. My focus now is on the long-term implications. The blue shift is a data point that will feed into our models of star formation and the distribution of volatile materials in the galaxy. If other star systems are producing comets with this level of supervolatile enrichment, it changes our understanding of the building blocks of exoplanets. It suggests that the icy material delivered to young planets in other systems might be far richer in the raw ingredients for complex chemistry than we previously thought. The blue light is, in a way, illuminating the potential for life's precursors to be seeded across the galaxy. I am also deeply involved in the analysis of the data from the two ESA spacecraft that may attempt a fly-through of the comet's tail. While a direct flyby of the nucleus is impossible, passing through the coma and tail would allow us to take direct, in situ measurements of the gas and dust composition. This would be the ultimate verification of the blue light hypothesis. We could directly measure the concentration of carbon monoxide ions and ammonia, confirming whether the blue glow is indeed the result of their photoionization. I am eagerly awaiting the results of those potential maneuvers, as they represent the next great leap in our understanding of this object. The sheer volume of data we have collected in the last few months is staggering. Every day brings a new image, a new spectral reading, a new data point that challenges our existing knowledge. The blue shift is the most dramatic visual evidence of the comet's alien nature, but it is just one piece of a much larger, more complex puzzle. I look at the blue glow and I see not just a comet, but a piece of interstellar history, a chemical time capsule that has finally been opened by the heat of our sun. It is a privilege to be a scientist at this moment, to be one of the first to truly understand the chemistry of a world that was born under a different star. The blue is fading, but the knowledge it has given us will last forever. The final analysis of the blue color is leading us down a path of deep theoretical consideration regarding the state of matter in the interstellar medium. I have to consider how these supervolatiles, like carbon monoxide, could have survived the journey. In the deep vacuum of space, far from any star, the temperature is just a few degrees above absolute zero. At those temperatures, even the most volatile molecules are locked solid. But the interstellar medium is not perfectly static. It is permeated by low-level radiation fields and occasional shockwaves from distant supernovae. I believe that the blue color is the final, spectacular release of material that was only barely holding on. The slight warming as 3I Atlas entered our solar system was the final straw, triggering a cascade of phase transitions that led to the massive, blue-glowing coma. I am also considering the implications for the controversial idea that 3I Atlas might be a fragment of a much larger, shattered interstellar object. If the blue color is so intense, it suggests a large, fresh surface area is being exposed. Could the cryovolcanism have been triggered by a recent, low-velocity impact in the outer solar system, exposing a massive, volatile-rich interior? The blue light would then be the signature of a catastrophic event, not just a gentle warming. This is a hypothesis that requires more data, but the intensity of the blue is certainly suggestive of a violent, rather than a gradual process. The color shift, in its entirety, is a narrative of destruction and revelation. The red crust was destroyed, revealing the green dicarbon, which was then overwhelmed by the blue glow of the supervolatiles. I see it as a process of unmasking, where the sun is peeling back the layers of an alien world. The blue is the deepest layer we have seen so far, the most pristine, the most indicative of its birth environment. I am confident that as we continue to analyze the spectral data, we will find even more subtle chemical signatures hidden within that blue light, faint lines that will point to even more exotic molecules. The work is just beginning, and the blue comet, 3I Atlas, is the key to unlocking the secrets of star systems far beyond our own. The blue is a temporary phenomenon, but its scientific legacy will be permanent. I have to emphasize the sheer scale of the energy involved in producing this blue light. For the carbon monoxide to be photoionized, it requires a significant input of energy from the sun's ultraviolet and X-ray radiation. The fact that the blue glow is so bright means that the rate of sublimation and subsequent ionization is enormous. I am talking about tons of material being ejected every second, a constant, powerful stream of gas that is being chemically transformed by the sun's energy. This is not a passive object. It is an active, dynamic chemical reactor. and the blue color is the exhaust plume of that reaction. It is a humbling sight to see the power of our sun interacting with a piece of matter that has never before felt its warmth. The blue is the color of a cosmic awakening, a billion-year sleep finally broken by the energy of a new star. The final piece of the puzzle, the one that ties the blue color to the comet's ultimate fate, is the depletion of its volatile reserves. The blue light is a sign of a massive, unsustainable loss of material. The comet is literally burning itself out as it passes through our solar system. The blue glow is beautiful, but it is also a sign of the object's imminent return to darkness. Once the supervolatiles are gone, the cryovolcanism will cease, the non-gravitational acceleration will diminish, and the comet will become a dark, inert lump of rock and heavy organics, perhaps with a faint, residual red crust. I am observing the final, glorious act of a cosmic traveler, and the blue color is its spectacular, temporary swan song. I will continue to track it, to analyze every photon, until it disappears back into the interstellar void, carrying its secrets with it, but leaving us with the profound knowledge that its blue light has revealed. The blue is the color of a new frontier in cometary science. I am also keenly aware of the need to differentiate the blue color of the coma from the blue color that can sometimes be seen in the ion tail. The ion tail, which is always blue, is composed of ionized water molecules and other fragments that are swept directly away from the sun by the solar wind. This is a standard cometary feature. What is unique about 3I Atlas is that the coma, the cloud of gas immediately surrounding the nucleus, is also exhibiting this blue hue, and it is this coma-based blue that is so strongly indicative of the carbon monoxide and ammonia. The coma is where the action is, where the sublimation and the initial ionization are taking place. The tail is merely the aftermath, the material that has already been swept away. I am focusing my attention on the very heart of the blue glow, the region closest to the nucleus, because that is where the most fundamental chemical processes are being revealed. The blue is a gradient, a spectrum of activity that starts at the nucleus and stretches for millions of kilometers into space. The scientific community is now working to model the exact ratio of carbon monoxide to water ice that would be required to produce the observed intensity of the blue light. My preliminary calculations suggest a ratio that is significantly higher than what we see in our own solar system's comets. This is a powerful, quantitative piece of evidence for the alien nature of 3I Atlas. It is not just qualitatively different, it is quantitatively different. The blue color is a direct measurement of the chemical dissimilarity between this interstellar object and our native comets. I am running simulations now, trying to recreate the conditions in the comet's home star system that would lead to such a high concentration of carbon monoxide. It is a complex problem, involving the temperature and density of the protoplanetary disk from which it formed, but the blue light is the constraint that guides my every calculation. I have also been collaborating with researchers who are looking at the polarization of the blue light. The way light is polarized can tell us about the shape and size of the particles that are scattering or emitting it. If the blue light were purely due to the scattering of sunlight by tiny dust grains, the polarization would have a specific signature. If it is due to the emission from ionized gas, the polarization signature is different. The initial results from the polarization studies are strongly supporting the gas emission hypothesis, reinforcing my belief that the blue is a chemical glow, not a scattering effect. This is the kind of cross-disciplinary verification that I find so satisfying in science. The spectral data, the non-gravitational acceleration, and the polarization studies are all converging on the same conclusion. The blue color is the signature of a massive, volatile-driven outburst from an interstellar nucleus. The sheer volume of the blue glowing coma is also a challenge for our observation techniques. The coma is so dense and so bright that it is actually obscuring our view of the nucleus itself. I cannot directly see the ice volcanoes, the vents from which the gas is erupting. I can only infer their existence from the effects they are having on the coma and the comet's trajectory. The blue light is a double-edged sword. It is the key to understanding the comet's chemistry, but it is also a veil that hides the physical processes at its heart. This is why the potential fly-through of the tail is so critical. If we can get a direct sample of the gas, we can bypass the obscuring effect of the coma and get a clearer picture of the nucleus's activity. I am also considering the long-term stability of the blue light-emitting molecules. Once the carbon monoxide is ionized, it is highly reactive and quickly fragments into other molecules. The blue glow is, therefore, a very transient phenomenon, a chemical reaction that is constantly being renewed by the sublimation of fresh material from the nucleus. The fact that the blue color has persisted for weeks, even as the comet moves away from the sun, is a testament to the enormous reservoir of volatile material that is still locked within the nucleus. I estimate that the comet has lost a significant fraction of its total mass during this outburst, a loss that is visually represented by the fading, but still persistent, blue glow. The blue color is a profound reminder of the diversity of the universe. We have spent decades studying the comets of our own solar system, and we thought we had a good handle on cometary chemistry. But 3I Atlas, with its extreme volatile enrichment and its spectacular blue glow, has shown us that there are entire chemical pathways and compositions that we had never considered. The blue is a sign that the universe is full of surprises, and that the process of star and planet formation is far more varied than our local sample suggests. I am excited to see what the next few months of data analysis will reveal, but for now, the blue light of 3I Atlas is the most compelling piece of evidence we have for the alien nature of this extraordinary cosmic visitor. The blue is the color of discovery. The final, and perhaps most philosophical, aspect of this blue shift is what it tells us about the fate of interstellar objects. 3I Atlas is a survivor, a piece of another star system that has traveled across the vastness of space. But its encounter with our sun is a destructive one. The blue light is the sign of its chemical demise, the consumption of its most precious, pristine materials. It will leave our solar system a different object than it entered, stripped of its most volatile ices, a darker, less active traveler. I see the blue glow as a kind of cosmic sacrifice, where the comet is giving up its secrets in a final, brilliant display of light. I am grateful for the opportunity to witness this event, and I know that the data we have collected will inform cometary science for generations to come. The blue is a fleeting moment, but its impact on our understanding of the cosmos is permanent. I am now working on the final, detailed spectral maps of the coma, trying to isolate the exact regions where the carbon monoxide and ammonia are most concentrated. The maps show a complex, asymmetrical structure, with the blue light being brightest in the jets that are pushing the comet off course. This is the ultimate confirmation of the link between the cryovolcanism, the non-gravitational acceleration, and the blue color. The blue is not uniform. It is concentrated in the areas of most intense activity. I can literally see the chemical engine of the comet at work, and it is a beautiful, violent, and profoundly alien sight. The blue is the color of a scientific triumph, a moment when we truly understood the heart of an interstellar world.